So, I'm going to introduce Dr. Christopher Shade, PhD. He specializes in biological, environmental, and analytical chemistry of mercury in all its forms and interactions with sulfur compounds, particularly glutathione and its enzyme system. He founded the only clinical lab in the world offering mercury speciation in human samples, and has designed cutting-edge systems of nutraceuticals for detoxification and antioxidant protection, including novel phospholipid delivery systems for both water and fat-soluble compounds.
Thank you,
Christopher. Thank you.
All right. See, here we get a little bit of claps instead of people. Yeah, I feel important. All right, so we're going to talk about delivery systems. Hopefully you guys know a little bit and then can get something out of this. This will all be about how you get bioavailability. Now, one of the things you get from this as well is water dispersibility. People will incorrectly say water solubility, but it's actually water dispersibility. All right, so as anyone in the industry knows, you got a little bit of a problem in pharmacokinetics. So pharmacokinetics is the entrance of any active into the blood over time with a given dosing form. So here you have hours after inhalation for concentrations of THC, and you see a very sharp spike up and a sharp spike down, and then it drifts away. Whereas for eating THC, you have a very slow, as all the people who've taken too much edible knows, if you've taken too much, the pain just keeps rising for 8 hours and then takes another, 16 hours to come back down to 0. So we need something that could bridge the gap. Interestingly, at the bottom we have the pharmacokinetics for inhaled THC for a 33 milligram dose, and then the pharmacokinetics for Sativex in a 33 milligram dose. So Sativex was attempting to get intraoral absorption of the actually Sativex is a pretty crude product. It's just cannabinoids dissolved in ethanol and propylene glycol. Now these are permeation enhancers, and you'll get some of the intraoral or sublingual absorption, but not a whole lot. So remember, as you see this, you're coming to your peak blood levels around 90 minutes. So that's better than peaking at 8 hours, but it might be better to get us something that would come up and could peak between 30 and 50 minutes and then come down over the next 2 hours. So that's what we'll be talking about. We're going to look at the pharmacokinetics of a nanoemulsion formula, and then we'll talk about what to look for when people are making nanoemulsions or any nano type of product in the cannabis space. And so bioavailability is why we're doing this. And bioavailability is defined as the proportion of a drug or any other active that enters circulation when introduced into the body and is so able to have an active effect. And I did your classic elephant in the room cartoon here because in the CBD world especially, and in the THC world, everybody's arguing over these little points, especially in the CBD world. Like, it's so annoying. Oh, I have a better, entourage profile than these other guys, and oh, mine's from marijuana and not from hemp. And there you're really just talking about THC to CBD ratios. You're not talking about any real difference in ability to get CBD into circulation. Bioavailability trumps those little arguments by so much it's ridiculous. And I feel like this elephant. Even if I stand in the middle of the room talking, everybody just ignores me because it's too sciencey for them. Except some of you guys will know what we're talking about. So in bioavailability, there's two measures, absolute and relative bioavailability. And so absolute bioavailability would be a comparison of an IV of a compound to some sort of oral. And so the IV, you immediately go up to your full concentration and you start falling. And anything introduced orally is going to be some fraction of the IV bioavailability. There's nothing more bioavailable than a needle. And it'll have different times of onset, but then the decay kinetics will be similar to the IV. And so it's a ratio of your dosage form to IV. So that's absolute bioavailability, and then there's relative bioavailability. And relative bioavailability would be two similar products compared to one another. So two orals. So we're going to look at the bioavailability and, well, really the pharmacokinetics, that's the blood concentration over time, of an oral CBD dose versus an intraoral nanoemulsion dose. So you have the higher bioavailability versus the lower one. So here this will be, one form is 5x more bioavailable than the other. Both are important, but not always measuring bioavailability can give you absolute bioavailability. So most of the time we're looking at relative. So there's a couple ways to get bioavailability studies. There's human uptake studies where you're going to dose somebody, you're going to port them up, and you're going to take blood samples over time. And that's the gold standard. Then there's animal studies where you're going to dose up a bunch of rats. You'll have your stoned rats, and you're going to take their blood over time. Maybe you're going to take organs. The nice thing if you're just doing pharmacokinetics is you don't have to sacrifice an animal. You just take their blood. And then there's another one. Hopefully this is the right. Oh, there we go. Look at that. It fixed itself quickly. There's another one called a CACO2 GI permeability assay. And we'll talk about that, and that you make a model of the GI lining, and you put your substance on one side of that, and it travels across this model GI lining, and you measure it on the other side. So you get a rate of transmission across this GI lining. So you can do absolute or relative with humans or animals, and CACO2 is going to be relative only. You'll be using that for comparing different variations of your formulation or looking at comparisons between different products. So, cutting to the chase and then working back into how we did this, let's look at pharmacokinetics of a nano-emulsified CBD versus just a CBD dissolved in hemp oil. And so CBD just dissolved in hemp oil, and this is like all the hemp out there on the market. If it's Charlotte's Web or Elixinol, just think CBD dispersed or dissolved in MCT oil or sunflower oil, olive oil. You're going to have these kind of kinetics where you're not even able to measure anything in the blood in 25 minutes, and then it starts at 50, and here's 70 and 110, and you have your peak around 110 minutes. And your total, or your absolute level in the blood is pretty low. Now, versus a nano-emulsified form, and my company is Quicksilver Scientific, and that's our Colorado hemp oil. We also make products for Holos Health and an MLM called Prime My Body. And here, in 25 minutes, you're almost at your peak concentration. And in fact, when I had these reanalyzed when we built out our own lab, these were done at University of Colorado at the Children's Hospital Tox Lab. When we had these reanalyzed, this point was actually up there, showing that we peaked at 25 minutes. So somewhere in this region you're peaking, which means there's immediacy to it. And the total difference for this whole time period, it was 5.33x increase in absorption. All right, we're going interactive.
Are these both digestive, or is one sublingual?
Okay. All right, well, first of all, this is a 10-person, two-way crossover study. So we get 10 people in a room, almost like we have here, and one day you're going to take one form, and we're going to measure blood. And the next day, we're going to take another form, and we're going to measure blood. So this, he was asking if this is digestive or intraoral. Now, the way that we did it was to disperse the CBD in hemp oil and put it in capsules and give them that. versus the nano-emulsified form was held intraorally and swallowed. So what he's bringing up is, would you have absorbed all that intraorally from just the CBD and the hemp oil? I'll tell you unequivocally, no.
Or the other way around, would you perhaps digestively?
Digestively, we've done some other pilot studies where it's not as fast, but the total amount in is almost the same. It'll look more like that. Yeah. Because there's this aspect, if you make a nanoemulsion right, these nanoparticles are small enough to go right to the capillaries, right to the spaces in the oral epithelia and go into the capillaries right below. And so, you know, this is just the demographics of the 10 people. It was roughly half male, half female, over an age range. Not too important. And then, as I said, in relative bioavailability, you'll look at each time point and you look at the ratio of you know, how many fold higher bioavailable the product was at that time point. Now, because there was nothing in the blood at 25, we don't have that ratio for the 25 minute, but at the 55 minutes, you're about 40x the blood levels in the nanoemulsion versus the oil, and then you move, you know, it moves down over time. It goes 40, 13, 7, 5.9, 5.3. And 5.33 is for that whole roughly 3-hour time period. All right, so what are these nanoemulsions? What are the different types of nanoparticles that are giving us this higher bioavailability? Now, the way that we make things is with phospholipids, though we do use some other co-surfactants with that, and different oils. Now, you'll hear the term often liposome, and if you go over to the Quicksilver Scientific booth, you'll see some things are called liposomes, like there'll be a B complex or a B12, and that's a liposome. And then you look at the CBD, and that's a nanoemulsion. So what's the difference? When you take phospholipids and disperse them into water, and then put them under shear, this is sort of a slicing that breaks them down into small spheres, they'll form these things called liposomes or liposomes. And if you look at it, if you remember back to biology, the cell membrane is a phospholipid bilayer. And that's exactly what these are. These are little cells. It'll be a sphere with a water core inside. And so if I'm doing a water soluble, I want my water soluble vitamin or compound in here. And then these little spheres can diffuse through my oral mucosa or the upper GI right into circulation without needing an uptake mechanism like a transporter. Now, if we're delivering not a water soluble but a fat soluble like CBD or vitamin D or vitamin A, then we're going to make a nanoemulsion. And we're going to have a carrier oil like hemp oil or MCT or even the terpenes. These become carrier oils. The carrier oils are just an oil that can dissolve the cannabinoid. But then we're going to encapsulate that carrier oil with the active, in this case a cannabinoid, in a monolayer of phospholipids or other surfactants. So the nanoemulsion has an oil core to transport and carry an oil soluble, and a liposome has a water core to carry a water soluble. So let's go to this one, makes it a little easier to understand. So if we look at something like Charlotte's Web, and Charlotte's Web, I mean, this is a nice plant, and it's a nice, simple, first-generation product. You've got your cannabinoids dissolved into an oil matrix. Now, if we take that oil matrix and break that down into tiny droplets that we disperse into a water matrix and we stabilize those droplets with our surfactants, that's what the nanoemulsion is. So that's the difference. Now, products like this, and I just want to show this slide because I want to show this thing called a chylomicron, because sometimes people get worried about the term nano. You know, so who here is thinking, wow, nano, maybe that's bad? Does anyone want to admit to that? No one wants to admit to that. But if you give this to someone and they say, well, aren't nanoparticles bad? Don't they, do bad things to you or bad in the environment? Mineral nanoparticles are. Now, the word nano just means that the particle or sphere is less than 100 nanometers. Now, that's important to us because that's the size at which you start getting intraoral absorption. And optically, that's the size where the emulsion becomes clear. But just being in that nano range is not a problem for a lipid-based nanoparticle. Now, if we are talking about something like titanium dioxide, then that's a bad thing. It can get into the body and be very difficult to remove. But for us, this is a chylomicron. This is how you move dietary fats from the GI tract out to your cells. And it looks very similar to a nanoemulsion because it's made out of phosphatidylcholine and it's got a core of oil. And those go down to 70 nanometers, so those are lipid nanoparticles themselves. And the body has all kinds of enzymes called phospholipases for dealing with these, for taking them apart, for using the substrates in different parts of the metabolism. And in fact, phosphatidylcholine is a nutrient itself, and we sell a supplement that is just phosphatidylcholine that's used for liver health and brain health. It can become choline, it can feed the membranes and the bioflow of the liver. And it can feed all of the cell membrane. So phospholipids, especially phosphatidylcholine, the one that we use, are a really healthful thing. This is just another visual of what a particle would look like. These are the water-soluble heads of the phospholipids with their tails tucked in. So you see that red would be an oil core in the middle. And as I said, if you make these small enough, you can get intraoral transmucosal delivery. This is a graphic of a guy wiping some substance on his inner cheek, and things are passively moving through this epithelium down to these blood vessels. But in order to do this, they have to be small enough particles to have what's called transcellular delivery, where they sneak in between the cell membranes in the junctions between each cell down through there. That's how you get fast uptake. But to do that, you have to be pretty small. And the smaller you are, the better the uptake. Let's skip through that. Now, how do we differentiate different liposomes and emulsions? The easiest way to do it is based on size. Now, there's large particles and small particles. In the liposomes, they look at layering and size. And in a liposome, this would be called a multilamellar vessel. A lamella is a layer. So when you first blend together the phospholipids in a water phase, you're going to get this thick emulsion with these large structures called multilamellar vesicles. These will be anywhere from 300 nanometers to 5,000 nanometers, and they will be thick and pasty looking. As you get them smaller, they start looking like milk. It will be fluid and milky, and they'll be in the 1 to 300, maybe 400 nanometer range, usually 2 to 400 nanometers. That's called a large unilamellar vesicle. And the small unilamellar vesicle is 20 to 100 nanometers. This is where we want to be. That's where you get intraoral absorption. And if we look at data from the literature, this was a pharmaceutical, this is out of the sort of the academic pharmacy literature. They were making liposomes with specific sizes and seeing what the uptake was. And so this compound gives you no uptake without liposomes. And incidentally, this is one in a CACO2 model, so one of those model GI tracts. And then going from 236 to 168 to 97, 79, 64, and 50, you see these bars get higher and higher, representing more and more absorption. And it's really in this sub 100 nanometer range where you really get the fast uptake. And we'll show you our data seeing the same thing. All right, so when we make the CBD nanoemulsion, and we also do this for THC CBD blends, but we license it out to manufacturers. So if you have a MIP and you're a finished product manufacturer, you can license this technology. But for us as a company, we sell the CBD. Here's an average batch. It's 18.4 nanometers mean size. They usually hover, between there and up to 30 nanometers. But that's part of our specification for each batch. So each batch can't be larger than that. All right, so we showed you the blood uptake using this nano emulsion technology. And now I want to show you more CACO2 studies. Because as more and more products come out there and say, oh, we're nano this, we're nano that, you have to be able to evaluate the products. And you're going to have to be able to evaluate their data. How do they prove that they have higher bioavailability? Because in this industry, it's like blah, 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 blah. I've got this, I've got that, nobody's got any data. So the way these CACO2 models work, and this will be the most likely thing that you'll see because, it'd be $10,000 to $20,000 to run, several formulations at once versus a human study, that was more like $30,000, $40,000 for 10 people. And so when you're iterating through, you'll be using CACO2s. And in the CACO2 model, you have a membrane, basically like a filter that you seed intestinal cells onto, and they grow to confluence, and then they polarize so that they have a membrane on one side that's like the inner membrane of your GI, and on the other side, it's like the membrane on the blood side of the GI tract. And so again, you put stuff in the top, these little CBD molecules, and they will diffuse through here, or they'll have active transport, depending upon what works on those molecules, and you'll be able to measure them down here. And the speed at which they come across is what you're going to measure. You're going to measure this concentration over time. It'll be growing with time. So here's an example of CACO2 using liposomal vitamin B12. And I told you in the literature, as you get smaller, you have higher uptake. At above 100 nanometers, the uptake is negligible. So this is the same formulation of liposome, but we made them at 3 different sizes, 138, 80, and 50 nanometers. And remember I said, around 100 is where you start to get real fast uptake and good uptake inside the mouth. And 138 is no better than the control. And then 80 and 50, you get faster and faster uptake. Now, these 3 were all at 50 nanometers, but it was 3 different membrane compositions. So if you don't get the membrane compositions right, you also don't get the uptake. This was the same kind of study, but using glutathione liposomes. And here we just compared them to 5 other liposomes on the market. And there'll always be a control. Back in the B12, that was the control. So you have to be better than the control to be working. And so you see 138 nanometers is no better than control. All right, give me 1 minute here. You started me 8 minutes and you have this going on during a cocktail hour. And this is just correlation between that and a blood uptake study. So CACO2 do correlate. They can be used to compare different R&D things, compare your product to other products. There's a lot of ways that you can do them. But when you do see the products that come onto the market and they say they're nano, if they're not transparent, they won't be nano. This is a 70 nanometer product. These are 300 nanometer products. This is another one. It's also very hard to do this with CBD and all cannabinoids. And this is what's said to be a liposomal CBD. And when you put it in a centrifuge, it breaks into gums, phospholipids, and the hemp oil. So this was never a stable nanoparticle at all. It wasn't even nano, but it wasn't even stable. So they should be transparent. You should be able to drop them in water, and it'll be a pretty transparent dispersion in water if it is nano. And that's how you'll be able to tell, and you should ask them to see their data. So I will cede the stage now, and if you have questions, maybe they'll let me answer them, or maybe you'll ask me over at the Quicksilver Scientific booth.
Thank you. Anybody want to do a quick question?
Yeah.
Yeah.
So how do you distinguish between a liposome and a micelle or a nano emulsion for your actual product? Are you doing electron microscopy?
Oh, yeah, I didn't really have enough time. I could show you. I have all kinds of transmission electron microscopy of liposomes and nanoemulsions. Micelles and nanoemulsions are going to be smaller. Liposome will never get below 20 nanometers, but I've seen them at that. And so in the electron microscopy that we do at CU, you can barely see the bilayer, the sort of black, white, black of the liposomes. And then when you get down to the nanoemulsions, you don't see that black, white, black in the membrane. It's just black heading into that center. And they're a smaller sizing. A micelle will be the smallest of all things. But, I mean, it depends. There's sort of a mushy line. Once you start loading more oils into a micelle, it starts becoming more of a nanoemulsion. So it's a combination of knowing what the chemistry of the inputs are and what the size is and what the electron microscopy tells you.
Okay, so you are demonstrating that you have a nanoemulsion versus a liposome.
Yeah, yeah, yeah. Yeah, I have them. If you come over to the booth, I can show you what some of those look like.
I think I was misinformed.
Everybody is.
I thought liposomal encapsulation was to help with the drug delivery into the cell.
Well, there's two things. There's getting into circulation and then getting into the cell. And one of the things with a phospholipid-based liposome is they do have ability to fuse their membrane with the cell membrane and help intracellular uptake. Though it's not like it just opens it up and dumps the drug in there. There's some interesting interactions where you'll see transporters come into play even though there's this fusion mechanics. But with cell cultures and liposomes and glutathione, there's a 100-fold increase in intracellular uptake off of just aqueous glutathione. But first we got to get it into the blood. So your particle has to be able to get into the blood and then help you get to the cell. So some of these are breaking down as they're getting in, but some of the particles are probably getting in intact and having some circulation.
So the second part of, I guess, all of that is, cannabinoid receptor sites, aren't they on the outside of the cell wall? So
Yeah.
would it be not beneficial to have it liposomal encapsulated because you want to break
this
apart
becomes a
before-
bit of a we don't know discussion. Like, oh well, mechanistically that shouldn't work. Like I said, these things break apart as they go into the blood. Some of them stay intact, but even in the glutathione uptake, they found that the transpeptidases that are on the outside of the membrane were totally involved in this higher uptake. And it might have been, there's water layers, hydration layers around cells and around particles, and maybe those layers are able to be breached better when the phospholipids are involved. But there is an interaction with the cell membrane receptors and transporters, but it's still facilitating a higher uptake. So it's not like it just sneaks through. That was some of the ideas in liposomes in the beginning, that it just sneaks into the cell, but it doesn't seem to be the case.
So it seems like there needs to be a second part to the study. Bioavailability is only one part of it.
Then there's the biodynamics or the pharmacodynamics of it. And the pharmacodynamics, I can assure you, are really strong. Especially, you can really easily measure that with the THC by people's stone effect. But with the CBD too. I mean, everybody has that sympathetic letdown very quickly. And for pretty small doses, 12 milligrams twice a day, you get a really strong systemic effect, especially in people with chronic inflammatory disorders like mold exposure cases and Lyme disease cases. So we know the dynamics are working, and we're trying to work. We're doing some brain scans. Voc Neuroscience has a real nice Quig-Loretta system that's quantitative electroencephalograms. And so we're doing some of the dynamic studies now. I mean, you go in the beginning just on symptomology, but we'll figure that out. It takes a long time to really work down to all the nitty-gritty.
Thank you.
All right? Thank you very much.